Assalamu alaikum wa rahmatullahi wa barakatuh. So we will continue our discussion on the filters. So in the last lecture we have seen how to design the low pass filters and high pass filter, and we have seen the Butterworth filter characteristics and what is the Salenki structure for a filter. Today we will discuss more about the filters, that is about the band pass filters. Okay, so we will discuss about the band pass filters. So what do you mean by this band pass filters? Okay, what do you mean by this band pass filters? So band pass filters are the filters which allow the frequency in a particular range. For example, you can see that these filters are having a high gain during this interval, that is from FC1 to FC2 they are having a high gain. Okay, they are having high gain. So they are having high gain in the interval FC1 to FC2. You can see this, they are having the interval, they are having the gain in the interval FC1 to FC2. That means the gain is this much during this interval. And for example, for the frequencies less than FC1, the gain is very low gain, that is, the gain is very low. And for frequencies which is greater than FC2, also the gain is very low, the same thing. Okay, same, gain is very low. So it is having a high gain in between these two. So between FC1 and FC2 the gain is high. Okay, this kind of filters are known as the band pass filters. So before defining the characteristics, or before going into the design of the band pass filters, we will see what do you mean by quality factor. The quality factor is a parameter which is defined as the ratio of the sender frequency to the bandwidth. So this is the formula for the quality factor. That means it is the ratio of sender frequency to the bandwidth. For example, if you have a filter having a characteristics like this, and you have a filter with another characteristics like this is having quality factor Q1 and this is having the quality factor Q2. It means that you see here, this is the bandwidth of this filter, second filter, and this is the bandwidth of the first filter. This is bandwidth 1 and bandwidth 2. You can see that the bandwidth 2 is greater than bandwidth 1. So the quality factor is high for the filter 1. So the quality factor is an indication of the selectivity of the band pass filter, that is how much it is selective. For example, if you have a filter with high quality factor, that means that it will select only few range of frequencies, or it will, you can, if you want to focus on a particular frequency, or if you want to filter out all other frequencies, then you need a filter with very high quality factor. If you want to extract a single frequency, then you need a quality factor which is tending to infinity. So we can classify the filters based on the quality factor. So if you have a filter which is having a quality factor greater than 10, then it is very high quality factor. That means that it will select only a few range of frequencies, very sharp. That means it will be very accurate in selecting only a few range of frequency. Okay, or we can say that it will select only a few range of frequencies, and this kind of filters are known as narrow band filters. Okay, and if you have quality factor less than 10, then you can, it will be like the characteristics I have shown here. For example, you can say this is quality factor which is greater than 10, and this is the quality factor less than 10. You can see here the characteristics. So the bandwidth is high, so it is a wide band, or we can say the bandwidth is high, wide band filter. Okay, so these are all the filters. And the quality factor also, it is related to the damping factor. In the last lecture I have already defined what do you mean by a damping factor. It is also related to the damping factor. It is the reciprocal of the damping factor. That means collective factor is equal to 1 over damping factor. So we will see a problem based on this. You can see this question. A certain band pass filter has the center frequency 15 kilohertz. That means the F naught is equal to 15 kilohertz. That is the center frequency. If you take the filter like this, then the center frequency is here, okay, 15 kilohertz. And the bandwidth, that means you know this is FC1 and this is FC2. The whole range of bandwidth is nothing but 1 kilohertz. So if you know the center frequency and the bandwidth, now if you divide the center frequency by bandwidth, then you are now getting a number 15. Now determine the Q and classify the filter as the narrow band and wide band. Now you see this Q is greater than 10, so it is a narrow band filter. It's very good filter actually for selecting a particular range of frequency. Okay, I hope this is clear to you. Now this is the narrow band filter. It is a narrow band filter. It is because the quality factor is greater than 10. So if the quality factor is less than 10, then we can say that it's a wide band filter. Okay, its frequency selectivity is less in that case. It will select a very wide range of frequencies. The other one will select only a particular very small range of frequencies, very sharp in selecting the frequencies. So we were discussing about the filters which are active. So first of all, we will see how to design a a band pass filter. So I have already given a hint regarding this. You know that we have the low pass filter having the characteristics like this, and you know this is the low pass filter, and you know that we have the high pass filter having the characteristics like this. Suppose if I design a low pass filter with characteristics FC2 as the cutoff frequency, and if I design a high pass filter with FC1 as the cutoff frequency, this is the high pass filter, and if I couple, you see here I couple a high pass filter and a low pass filter. Both are cell and key type. Okay, both are cell and key type. We have already discussed what is cell and key type in the previous lecture. So I will give some input here and I will give some output here. Now what I am getting, actually I will get the product of this two. That means it is cascaded. That means I will be getting the frequency in frequency domain. I will be getting the product of these two as the output, so that my output characteristics will be like this. Okay, so basically this is coming from, this part is coming from the low pass filter and this part is coming from the high pass filter. So I have FC1 here and I have FC2 here. I have already explained this phenomenon in the last lecture also, but we have seen now a circuit diagram. So you see here this is a high pass filter. Okay, this is the characteristics of this high pass filter, and the cutoff frequency for this high pass filter is FC1, and this one, so this is the high pass filter. Now this is the low pass filter and it is having the characteristics like this, and the cutoff frequency is FC2. Now at the output, actually for the whole stage, for the whole filter, I will be having a characteristics like this. Okay, so this is the characteristics of the whole filter anyway. So this is a this high pass filter, the design of this high pass filter, you know how to design this high pass filter and how to design that low pass filter, everything you know very clearly. So if you know the design of a high pass filter and a low pass filter, then according to the bandwidth you can design. Okay, and what is the bandwidth of the filter? Bandwidth is equal to FC2 minus FC1, and what is the quality factor? F0 divided by bandwidth. So based on a particular quality factor, and if you know what frequency is the center frequency, okay, and what is the center frequency, for example, the center frequency, it will be like this. Okay, at the center frequency you will be getting the maximum gain. Okay, and at all other frequencies the gain will be less. So according to this design, you can actually make a high pass filter and a low pass filter. So this is a low pass filter. So by combining a high pass filter with a low pass filter, you are getting, actually this is nothing but the band pass filter. And what is this? FC high pass filter with a cutoff frequency FC1 and low pass filter with cutoff frequency FC2. Note that your FC1 is less than FC2. This is very, very important. Otherwise you will get a band reject actually, that we will see later. So I hope this part is clear to you. Now this is the characteristics you see here. It is a combination of the high pass filter that I have just explained now. So the blue color is actually showing the high pass filter. Okay, it is showing the high pass filter. It is showing the high pass filter, and the other one is showing the low pass filter. Okay, so this is the response. So you have the high pass filter and a low pass filter, and its combination is actually giving you a band pass filter, and this is the bandwidth. Okay, and bandwidth is nothing but FC2 minus FC1. Okay, and this is, and you know that for a this is for the high pass filter. This is the formula that you have already seen in the filter design of the high pass filter, and for FC2 the same kind of formula for the second filter. It is RA2, BA2, RB2 and CA2 and CA2, CA2 and CB2. So this is for the design of the low pass filter, and you should know that this cutoff frequency FC1 is less than FC2, and the center frequency is nothing but the geometric mean of this. Okay, the center frequency is nothing but the geometric mean of these things. Okay, so we got the center frequency also. Now this is the filter. So actually for the exam I will be asking either low pass filter or high pass filter design. Okay, I will not be asking the band pass filter and band reject filter now. If you know the high pass and low pass filter design, which has been explained in the previous lecture, then that idea can be used to design any filter. So I will be asking for the exam mainly about the high pass filter and low pass filter. Okay, but these I am teaching all these things because you should know about the different types of filters and how they behave. Okay, so we have seen these characteristics. Now we have another kind of filter. So these are all the class of filters which is coming under the Allen key type, and this can be designed with a Butterworth response. Okay, now another thing is that multiple feedback band pass filter. So you can see here, this is the another kind of design. This is a band pass filter. It contains, you know that basically this kind of circuit you have already seen. What is this circuit? Okay, sorry. What is this kind of circuit? For example, this circuit. You know that this circuit you have already studied. It is a differentiator, right? Differentiator. And what about this circuit? You have already seen this circuit. This is here, and here the capacitor in the feedback. And what is this? This is an integrator. So all of you should please understand that this, if you take the frequency response characteristics of integrator and differentiator, you can see that your differentiator is behaving like a high pass filter, and if you take the characteristics of the integrator, then you can see that it is acting as a low pass filter. Now you can see both here in this. If you take this filter response here, this part actually it is showing, you see, if you take this part, what is that? It is showing a differentiator basically, right? It is showing a differentiator. And if you take the another part, for example, if you take this part, okay, and the whole op amp and this configuration and this along this through this path, what is that? It is showing actually a integrator. So integrator, I told you, the differentiator, I will just show you, the differentiator is having a response of high pass filter. So before that, yeah, it is having a response of high pass filter. Okay, it is having a response of high pass filter. Differentiator is having a response of high pass filter, and the integrator is having a response of low pass filter. You see, it is having a response of low pass filter. So if you are properly choosing this R1 C1 and R2 C2 and R3, you can see there is R3 also, okay, and without R3 it will not work. Okay, what is the reason for that? Because if you have to do any circuit analysis for this, but we are not going into much detail. So you can see here that this is some frequency FC2 and this is some frequency which is FC1. Now this characteristics is showing actually a band pass filter, and this is the center frequency. So that is how it is combining actually an integrator and a differentiator basically. So please remember that integrator is acting as a low pass filter and the differentiator is acting as a high pass filter. Okay, so we are combining in parallel actually, you can see. So what will happen if you give very high frequency, if you give low frequency, what will happen? Your integrator, sorry, your differentiator capacitor is here, it will block it, okay, because low frequency will be blocked by the capacitor which is been shown here. So low frequency will be blocked by this guy. Now if you are giving high frequency, then high frequency actually it will get feedback, it will feed it back as a negative feedback. You see here it is a negative feedback. Because of the feedback, the gain actually, what will happen to the gain? The gain will decrease. So that means it is also blocked. That means the gain will be decreasing at high frequency because of this integration characteristics, and because of the differentiation characteristics at low frequency it will be blocking. Okay, so this is the type of filter which is known as the multiple feedback band pass filter. There are two feedbacks. One is a feedback through the resistor, one is the feedback through this resistor, that is the part of the differentiator, and this feedback is through the capacitor, is a part of the integrator. So at low frequency will be blocked by this guy, it will block this guy, this capacitor will block all the low frequencies, and the high frequencies will be feeded back. You see, the high frequencies will be feeded back through this capacitor. Since the feedback at high frequency is very high, the gain will be low. Okay, because when you feed back all the voltages, then what will happen? The gain automatically reduces. Okay, so all the voltage at the output, if you feed back all the voltage at the output, the gain will be reducing. Okay, now there are some expression for this. Okay, you don't need to remember all this expression. I will not be asking this for the exam, but this is for your understanding. Anyway, you see here the frequency, center frequency for this kind of filter. That means it will be showing a characteristics like this. This is F0, and it can be designed by using the R1 parallel R2 multiplied with R2, sorry, R1 parallel R3 multiplied with R2 into C1 C2, that is 1 over 2 pi into square root of this expression I am saying, okay, square root of R2 into C1 C2. And how it is working actually, this why I am taking R1 parallel with R2. Whenever I talk about this capacitor C1, if I talk about this capacitor C1, if you view from here, you are standing here, and if you see from here, and if the input is short circuit, that means if the input is grounded, you can see that this R1 and R2 is parallel. That's why, because this is, if the input is grounded, then you can see that R1 is parallel to R2. That's why you are connecting, you are considering the equation like this, and there is a derivation for it. We are not going to use the derivation. Now if I use all the capacitors and all the capacitor as the same, for example, if I make all the C1 is equal to my C2, then my expression will be reduced to 1 by 2 pi square root of R1 parallel R3 into R2 into C square. So that I can take the C outside, and the final equation will be like this. Okay, this is the final equation. So if I can change my center frequency. I can change my center frequency. How to change the center frequency? By changing R1, R2 and R3. If I change R1, R2 and R3, I can change my center frequency. Okay. Now what about the bandwidth? you see here that the bandwidth is basically it is, if I change the center frequency, and you know that the quality factor is equal to f naught by bandwidth. Okay. So, the value of the capacitor is chosen, and then 3 resistor values are calculated to achieve the desired values for f naught, bandwidth and a naught. So, all these are actually calculated R1, R2 and R3. Based on the R1, R2 and R3, you can actually fix the center frequency. And also through a big derivation, it is stated without the derivation, you can select the value of R1 as the quality factor you needed. For example, you are designing a filter with a quality factor of 100, then you just choose Q equal to 100. And if you want a center frequency of for example 10 kilohertz, then f naught is equal to 10 kilohertz, like that. So, if you know the Q and if you know this C f naught, then you can calculate the value. If you fix the value of C and if you fix the value of a naught, you can calculate the value of R1. Similarly, you can calculate R2. Similarly, you can calculate R3 also. So, you know that from this equation 1, this is 2, this is 3. From this equation 1, I can actually write my Q as R1 into 2 pi f naught into C into a naught. Similarly, from the second equation, I can write my Q is equal to R2 into pi into f naught into C. So, you see here I can equate, this is Q equal to Q. So, I can equate this also. So, if I do like that, if I equate these two by using this equation, you see, then what I will be getting, I can calculate what is the value of a naught. So, you see here that the value of a naught will be equal to R2 over 2R1. Okay, you do not need to remember all this proof, or you do not need to remember these formulas regarding band pass filters and band reject. That's I will be discussing that later. So, you can see here that there is another formula by using equation 3. This equation 3 is giving you the value of, it is giving you the value of R3. So, you know that the R3 is a resistor. So, always the value will be positive. So, this number should be positive, right? This number should be positive. That means that your 2 into Q square minus a naught should be greater than 0, or you can say that your a naught should be less than 2 into Q square. So, if you fix the quality factor, you have to fix the gain also in such a way that it should be less than 2 times Q square. If you do not fix like that, if you do not fix like that, it will not work, the circuit will not work. So, the main important point is that your gain is limited. The gain is limited by the value of the quality factor, This is the main only constraint. This is the one of the constraint or one of the limitation of this particular type of model. So, this is a model which is known as the multiple feedback band pass filter. Okay. So, this is one kind of filter. So, now this is a problem. Okay, I will not ask any problem related to the band pass filters and band reject, do not worry. So, but I will be asking the design of the low pass and high pass filters. So, please study carefully about it. Okay. Now, this is a problem which is from the textbook. So, determine by mistake I touched some more and it has gone, yeah. Okay. So, determine the center frequency, maximum gain and the bandwidth for the filters shown in the figure. So, this is a filter actually you have just studied now. It is multiple feedback filter. Okay. And why there is a multiple feedback? There is a feedback through the capacitor and there is a feedback through the resistance R2. Okay. Another one is through C1. So, there are two feedback, that is why it is multiple feedback. Now, how to find the F naught? Just use the formula. if you know all the R1, R2, R3, etc., you can calculate the center frequency. So I will just draw the frequency response of this filter. So the frequency response will be looking like this. Okay, so the F0 is equal to 736 hertz. Okay, then we have another ranges, this one, this frequency FC2, and this is FC1. Okay, now what is the maximum gain of this filter? The maximum gain of this filter is actually 1.32. You see here it is limited with the by a number. Actually it is 1.32. So you will get a maximum here. The gain is 1.32. So this is the gain, and it will happen at F0. It will happen at F0, the maximum gain, and you can calculate the quality factor. Okay, the quality factor is 4.16. So the quality factor means what? It's a quality factor means the F0 divided by bandwidth. So which type of filter it is? It is the quality factor is low, it is less than 10, so it is a wide band filter. Wide band filter. Okay, wide band pass filter. And the bandwidth is equal to F0 by Q, because if you know the quality factor is equal to F0 by bandwidth, then you can calculate the bandwidth as F0 by Q. Okay, that's it. Now this is the multiple feedback filter. Okay, now I will go through another kind of filter which is known as state variable filter. State variable filter is a special kind of filter. It contains basically three things. It contains a summing amplifier followed by an integrator, again an integrator. You know that an integrator is having actually this is the capacitor in a feedback. That's why it's an integrator. This is also an integrator. So how it is working, and what is this? This is a summing amplifier. So it will take one voltage from here, another voltage which is coming from the feedback. This is from the feedback. Okay, feedback voltage. Now you know that this is an integrator. So we should know first, integrator behave like a low pass filter. So if the frequency is low, I will just use a color, low frequency. For low frequency I will use the red color. So if the frequency is low, what will happen? It will allow all the frequencies, because this guy is behaving like a low pass filter. So it will allow, so this circuit will allow all the low frequency, and finally you will be getting some output here. But what will happen to this output? That's the main thing. This output will get feedback first. It will be fed back through this resistor, okay, R1. Okay, it will be fed back to the resistor, and it will be added, because this is a summing amplifier. You see, this is a summing amplifier. So because of this summing amplifier, this will get added. I will just delete this. Okay, so this will get added here. This will get added with the input signal. Input signal is coming here, and the feedback signal and input signal will get added. But the problem is, you know that this is a positive. For example, if the input is a positive input, you will get here negative, because you are connecting the op amp in a inverting configuration. Now this is negative, you will get a positive here. Now if you give a positive, you will get a negative here. So if you give a positive, you are getting actually negative. That means that your output is 180 degree out of phase. 180 degree out of phase. That means that if you give here Vin, your feedback voltage Vf will be some constant into minus of Vin, because you will be getting a minus sign. So what you are doing, actually you are subtracting Vin. You see here, you are actually getting a feedback voltage which is A into minus Vin. Okay, so you are getting actually a feedback voltage here which is nothing but minus of A into Vin. Now you see, you have the original signal as Vin and another signal as minus of A into Vin. If you add both of them, actually the total input which is appearing, the total input is minus, it will be Vin minus A into Vin. That means it is small now. Because of the small signal, what will happen? Your output also will be small. That means that your gain will be small. Okay, your gain will be small. Please one second, by mistake. Okay. So your gain will be small. So the gain will become small at low frequency. So what is happening here? At low frequency the gain is small. So I will just draw the frequency response here. You see here that the frequency, so the gain is small. So this is due to the integrator actions. So due to the integrator actions. Okay, it is low, it's the gain is small at low frequency. Okay. Now when the frequency become the overall gain is low at, it's not due to the integrator action, sorry, it is due to the summing amplifier action, sorry for that. It is due to, you are getting the low gain because due to the feedback you will be getting a 180 degree out of phase. So V out will be equal to something like it is low for the frequency less than FC1, for example. This is the cutoff frequency. Here also you can mention some cutoff frequency. So you can see that your gain will be low. It is due to the summing amplifier subtraction actually, because when you give some low frequency input, all this low frequency input will be there at the output, but it will be 180 degree out of phase. So all these get fed back and added by using the summing amplifier. Because of the summing amplifier, it will subtract by using this formula V in minus some constant into V in. Okay, that your overall output signal become small because your input, the net input is now small. So you will get the but here you see there is a problem here. You will get here a low pass signal that I have already told you, but where is your band pass signal? Your band pass signal is obtained here. Okay, and this is your high pass signal, and this is your high pass signal. Why it is your high pass signal? Why? You can get all the outputs. For example, you will get a high pass output, you will get a band pass output, you will get a low pass output. That means you can get all the high frequencies here, you will get the band frequencies here, and you will get the low frequencies here. Why it is getting like this? Because I told you when the input is at low frequency, the output will be 180 degree out of phase, and it will get added due to the summing amplifier, and you will get at low frequency the output will be very small. So the low frequency output will be very small, and then it is known as the high pass filter, because this characteristics will be like high pass filter. Now this is behaving like, this output is behaving like a band pass filter, and this output is behaving like a low pass filter. Now what will happen? You are getting at low frequency, you are getting something. You are at low frequency, you are getting a very small gain. But as the frequency increases, this is your integrator at some frequency. As the frequency increases, the low pass filter output reduces. This will reduces as the frequency increases. I will just use another color. As the frequency increases, the low pass output actually decreases. Because of that, the summing amplifier cancellation will be reduces. That means that this output will be increases. So that means that your high pass output will increases. Your high pass output increases means that there is an integrator here. Because of this guy, it will not allow, because integrator is a another low pass filter. So because of this integration action, you will not get very high gain at high frequency. So as the frequency increases very high, your gain will start decreasing, and this is the characteristics. That's why you are getting a response like this. So this will act as a band pass filter. So anyway, this is the working of this working principle of this kind of filter. So but the problem with this filter is that we cannot accurately design a high pass filter or a low pass filter, but we can design a band pass filter. To optimize, we cannot tune these filters. for a Butterworth response. It's very difficult to tune this filter for a Butterworth response. You know that for a Butterworth response, the DF must be, that means the damping factor should be equal to 1.414, and the quality factor is related to the damping factor as 1 by DF. So the quality factor should be 0.707. The quality factor now, which is less than 10, it implies that it is a wide band filter. So if you want to design a narrow band filter, this kind of filter usually will not respond well. If you want to design a filter with very sharp frequency response, it's very difficult to design by using this kind of filter. It is because of this criteria, because the quality factor is related to the damping factor with Q equal to 1 by DF. So the Q will be, if you choose the damping factor very high, then the Q is very small. So that's not a good design, that's why. Okay, so I will just explain using this figure once again. Okay, you give a high frequency, the high frequency, if yes, at high frequency what will happen, this is acting as a summing amplifier, this is an integrator, and this is also another integrator. At high frequency, the gain, at low frequency, I will just use a low frequency for example. If you use the low frequency, at low frequency, what will happen? This will allow all the signals. This will also allow all the signals, but the signals will be 180 degree out of phase. Okay, because if you give a positive, you will get a negative. So because of this will be get feeded back. Okay, so the negative and one is positive, and this gets subtracted. So the signal become low. That means that the output here also become low, and you will get a low response here. Okay, so this part actually behave like, the output here will be behave like a high pass filter. The output here, this will be behave like a band pass filter, because you see it is acting like this part is coming from here actually at low frequency. But now you will see at high frequency what will happen. At high frequency this signal will reach here anyway, no issue, but this will be small. So what will happen, because this is an integrator is a low pass filter, so this will be small, so that at high frequency the gain again will be small. So this is the response. Now you are actually cascading these two. So what will happen, the total output, it will be like a band pass filter. So band pass filter output is available here. So this is the band pass filter. Okay, and the band pass filter, and this is the high pass filter. This output actually behave like a high pass filter, and this output is behaving like a low pass filter. Okay, so now in this problem, determine the sender frequency Q and the bandwidth for the band pass output of the state variable shown, state variable filter. This is a state variable filter. So this is the formula for this formula for finding the cutoff frequency for the first part for the integrator. For each integrator, the cutoff frequency is 1 by 2 pi R4 into C1. Okay, so if all are equal, you see here that this is 1 kilo and this is 0.02, and here also it is 1 kilo and it's also 0.02. So for both of the integrator, the cutoff frequencies are same. Now if you choose F naught equal to Fc, your quality factor will be given by using this formula. You don't need to remember these formulas, and you can calculate the bandwidth. So you see the bandwidth is very small, and you are getting high quality factor. So you are getting high Q and low bandwidth. This is desirable for good frequency selectivity. You are getting a very narrow band filter. Actually, it's a narrow band filter. The quality factor is greater than 10. So it is a narrow band filter. So it is having high selectivity. This kind of filters are having high selectivity for frequency. That means what? If you want to select a particular frequency, you can use this kind of filters. Okay. For example, you have a signal which is mixed with many frequencies and you are focusing only on 1 kilohertz. So you design a filter with f0 equal to 1 kilohertz and you can just filter out those signal. Okay. So that is the state variable filter. And another kind of filter is a bichord filter. This is another kind of filter which is known as bichord filter. Okay. And bichord filter, it is having integrator. You know, the integrator is again a low pass filter. Then you have an inverting amplifier and again you have an integrator here. Okay. So this is having this integrator will give you the band pass response. Why? Because you see this is an integrator which is giving you, if you are giving a positive signal, you will get a negative signal, because if you give a positive, you will get a negative here, then positive here, and this is negative. Okay. So this will get again subtracted as in the previous case. So at high frequency you will get the signal will get subtracted. You are getting a positive signal and this output will become negative. So positive and negative will get subtracted. So the band pass output at this point will be small, so that you will be getting a response something like this with f0. So this is the band pass output. So you can, if you take the output from here, then it is a band pass output. If you take the output from here, it is a low pass output. Okay. Now I want to tell you one more thing. If you have a bichord filter, that bichord filter, how it is different from the state variable filter. And you know that the equation for the quality factor is f0 divided by bandwidth. So in a bichord filter, you can control the quality factor by changing the f0, but in a state variable filter, for example, if you take a state variable filter that we have discussed here, then you know that the quality factor is equal to f0 divided by bandwidth, and here your f0 is fixed actually according to the design, and you can have a tunable control on the bandwidth, and you can control the quality factor. So the quality factor is in the state variable filter is controlled by controlling the bandwidth. Okay, because the formulas in the design, it is everything is showing like that. Okay. So you have no control over f0, because once you designed the integrator, you are getting f0. Now after that you cannot change it. Now by controlling R5 and R6, for example, you see R5 and R6, you are getting a quality factor, and by using quality factor you are calculating the bandwidth. So the bandwidth is related to the quality factor. Okay, basically. So that's why that is the main difference between the bichord filter and this filter. In this filter, actually you can control the quality factor by controlling the center frequency. Okay, but we will not, I am just giving you just an idea. All the designs are not there, it's very complicated, and we will just see only the cell and key filter design for the Butterworth response for low pass filter and high pass filter that has been already discussed in the last lecture. Okay. Now that's about the bichord filter. Now we will see the active band stop filters. And what do you mean by this band stop filter? Band stop filter means what? It is having a response something like this. For example, this is the critical frequency and this is the FC2 and this is F0. At F0 the gain, it's almost 0. That means it will stop all the frequencies at F0 and it will allow other frequencies. Okay. So this kind of filters are known as the band stop filter. Since we are talking about the active filters, that means it contains amplifier or the active elements like transistors. So we will see the circuits with the op-amp. There are two types: multiple feedback band stop filter. We have seen multiple feedback band pass filter. How we have designed? multiple feedback, it contains integrator and the differentiator, just we see now, and this is the response of the differentiator and this is the response of the integrator, but the cutoff frequencies, you see the cutoff frequency for both are same f naught for example, but in this is the band pass filter, okay, but in band stop filter we will use the same notion, same kind of circuit, but the cutoff frequencies will be different. For example, I will just, you see the cutoff frequencies will be different. This filter will be showing like this. So this is a integrator and this is a differentiator response. Differentiator is a high pass filter and integrator is a low pass filter. So you are, if you are coupling, if you are spacing it, because this frequency is FC1 and this frequency is FC2. So if you are choosing, you see here the center frequency for band pass filter f naught equal to FC of integrator, which is equal to FC of differentiator. But here FC1 and FC2 are different. Here the cutoff frequency, it is here, okay, f naught, not cutoff frequency, it is the center frequency, okay. So that is the difference with the multiple feedback filter. So we will see the multiple feedback filter. So your multiple feedback filter, it is shown here. You see here that the structure is almost the same, but a small difference with the what we say, the multiple feedback band pass filter. You see here the multiple feedback band pass filter that we have already seen, the multiple feedback band pass filter, it is having an R3 and there is no feedback loop here because there is no resistor here. But here you see this is also this is a multiple feedback type. So this multiple feedback band pass filter is having two resistors R1 and R3, okay. So the working is almost similar, as I have told that this is a differentiator part and this is a integrator part, okay. So one is a differentiator part, another one is a integrator part. So this part is act as an integrator or a low pass filter, and the other part is acting like a high pass filter. So it is a combination of both this, and how this is combined, low pass filter is having a response like this and high pass filter is having a response like this. This is a low pass filter and this is a high pass filter. So I will get a band stop filter. So this in this band the gain will be less. So what is happening here? I will just give a logical explanation, not the mathematical analysis. At high frequency, for example, I will use a different color. I will use a low pass filter, so I will use a low frequency. At low frequency, what will happen? At low frequency, this capacitor will block everything. This guy, the signal cannot go here because of the capacitor, because the capacitor reactance at the low frequency will be high. So the gain will be low, gain decreases. This happening to the gain. Now at high frequency, what is happening? At high frequency, you see here that this capacitor, the capacitor which is like this C1, at high frequency, what is happening here? The feedback will be high. So feedback will be high at high frequency. So at high frequency, the feedback is high. So what will happen? Then the gain decreases. The gain decreases due to high feedback. Feedback will be high because the capacitive reactance will be small. So the capacitive reactance due to C2 will be small, and also C1 also will be small. Because of this high feedback, you will get low gain. So at what frequency you need all these things? Everything can be calculated based on the value of C1, C2, R1, R2, R3 and R4, okay. So these are all the controlling parameters. Anyway, we will not see much details about it, just see the logical explanation. Now another one is the state variable band stop filter. So state variable band stop filter, okay. So you see here, this is a state variable filter, and from the state variable filter that we have already seen, state variable filter, from that you can get low pass filter and high pass filter. And if you subtract these two, if you add, not subtracting, it is adding, summing amplifier, this is a summing amplifier. So what will happen, you see this low pass output will be like this, and this high pass output will be like this. Okay, if you add both, you will get some response which is equal to, which is like this. Okay, so this is at f0. So you will get a band pass filter. So you know that this, from the state variable filter will give you band pass, low pass and high pass, but you will take only low pass and high pass, and you will be given to a summing amplifier. If you add both of them, you will get the band stop filter. But you have to design the critical frequencies for low pass and high pass cleverly, then only you will get a. So how to design it? You know this low pass response and high pass response we have already seen. This is the state variable filter. We have seen that the critical frequencies FC, the FC is like this by using this formula. For example, it is 1 by 2 pi R4 into C1. Similarly, if you, so you can design the state variable filter. One state variable filter is giving you the, you have to design the state variable filter for the each integrator. Actually you have to use this formula, or you have to use this formula, but here in our case R4 and R7 or C1 and C2 will be different according to the frequency that we need. Okay, so that is the idea of the state variable filter. Now we will see a problem, band stop filter, and these problems I will not ask anyway. Please understand this problem for your knowledge. Verify that the band stop filter has the center frequency of 60 Hz and optimize the filter for a quality factor of 10. So you see here, this is the design of the filter, and f0 is equal to, as I have told you, f0 is equal to 1 by 2 pi R4 into C1. That means I will take, this is coming from here, and so I will take this resistor and this capacitor, 1 by 2 pi. And another is I will just use this also, you see, and it is coming from here, that is this and this one. Okay, so I am getting 60 Hz. Now you can obtain the quality factor by choosing R6 and then calculate R5. So here you see the quality factor is having this equation, and your R5 is having this equation, and based on this equation we will be calculating the value of R5. Okay, and if you choose R6, this is just an assumption, assume R6 is equal to 3.3. Why I am using 3.3? It is a standard value for the resistance. Okay, 4.7 kilo ohm, then 1 kilo ohm, okay, 2 kilo ohm, all these are standard values. Okay, now R5 can be calculated using these formulas. So all these formulas are there. So if you want to derive all this formula, it is little bit complex circuit analysis. You may need the Laplace transform, convert the circuit into Laplace transform domain, and then you need to write the Kirchhoff laws, and then you need to solve this, and you have to compare with the standard equations, and then lot of things has to be done. Okay, so that's why we are not going to the much details about it. Okay, it will be very difficult for you, but all of you please understand. Now you see here R5 is equal to 95.7, and 95.7 kilo ohm resistance is not a standard value, so usually chosen value is 100 kilo. 100 kilo is standard value which is available in the market. Okay, so I hope that you understood the basic notion of the filters. Okay, so that's about the filters. So please be thorough with the first lecture, which is regarding the band pass filter, sorry, not band pass filter, which is regarding the low pass filters and the high pass filters, I will be asking for the exam. But for the band pass filter design, nothing, I will not be asking for the exam. This lecture has been conducted for your knowledge. Okay, inshallah we will see in the next class. Okay, thank you.